So in this session, I will talk about what are quantum computers and how they are different from classical computers. We will also discuss what are qubits and how they are different from classical bits. We will also talk about quantum gates and algorithms, and I will explain how quantum algorithms are different from the classical programs or classical algorithms that we think about in certain ways. Though this thing will become actually clearer when we go on to actual algorithms during the course, but it's nice to have some discussion before we delve into actual algorithms. And then I will also talk about some of the applications of quantum computers, and at the end we will talk about why we think that quantum computers are, better or faster than classical computers. I mean, what are the rationales and where we think things are heading. Okay, so let's start with a discussion on quantum computers. Okay, so a quantum computer, like classical computer, is a device that is intended to process information. So broadly speaking, it's same as classical computer in this respect, that the goal is the same. The difference comes from what goes on at the hardware level, and of course that difference then also translates to the speed of processing of quantum computers. So that's why we are investing a lot of efforts into building and understanding quantum computers. But if we think about a sort of a device level definition for quantum computers, we can say that okay, this is a device where we represent information on quantum systems. And I'll shortly talk about what quantum systems are. So instead of representing information on classical bits in terms of ones and zeros, we represent information on quantum systems, which can be more than ones and zeros. And then we should be able to process this information. So the other part of these quantum computers is this, that we are able to process this sort of quantum information, and then we should be able to measure the information that has been processed on these systems. So these parts of these quantum systems, quantum computers, will become clearer as we go on. But this is certainly something that we can imagine in a way that there is one or many quantum systems, and a quantum computer is a device where we are able to represent information using these quantum system, and then we're able to do some operations or processes on these quantum systems. That information is processed. There are some operations that we are able to do on this information, and then at the end we should be able to read off this information from those quantum systems. So this is a quantum computer in a nutshell. And so when we try to understand quantum computers, so in addition to understanding these steps of representation, processing, and measurement, we also need to be able to understand the quantum system. So a quantum system is something, which which is isolated from the rest of the world, at least at this stage of this course, and it obeys, the laws of quantum physics. And if I talk about just, precise examples, we can think about a hydrogen atom that has a proton in it and an electron around it. And this quantum system, for example, I hope that most of you know from modern physics, can have several energies in it. This system can be, at several energy states. For example, it can be in ground state, which we call n is equal to 1 state. It can be in the excited state. For example, this electron can jump to the next shell, and it can be, in another excited state, and so on. So a quantum system, this system can exist in several energy states. But actually, it's capable of, more than this, which is sometimes not that much emphasized in earlier courses, and that is that the system cannot only exist at this level or at this level or at this level, but it can also exist in a superposition state, that it is in some state, that if I represent it with this, sort of mingling of these two levels, that the system is in some state that when we measure it, it either collapses to this n is equal to 3 state or n is equal to 2 state. So when we measure, it is going to be either here or maybe here, but the system exists in a state which is neither this nor that. So that superposition state, is something which is not available when we talk about classical systems. For example, our classical bit, if you think of the classical bit as a magnetized region on your hard drive. For example, there are a lot of these individual regions on this device, and if I think about one, if it is magnetized in one way, we can say it is 1. If it is, magnetized in the opposite direction, we can label it as 0. Or if we, think about actual logic gates in which there are transistors, if it is a high voltage, for example, 4 to 5 volts, we can label it a logical 1. Or if it is, at a voltage state between 0 and let's say 0.5 volts, we can label it as 0. But we don't have anything, okay, the system can exist in a superposition of 0 or 1. And in actuality, if the system is, for example, neither is in 0 or 1 state, we say the system is in error. For example, if somehow the output of some transistor is like at the boundary of 0 and 1, we can think of it as an error. But here, this is a desired property of the system, that the system is present in a superposition state, that it is neither this energy level nor this level. But when we do measure the system, it collapses to either this one or that one. So this is, one example of a quantum system. Another example of, so let me label it, for example, an atom. Similarly, you can think about molecules and so on. So another example could be your LC circuit. So for example, you have an inductor and a capacitor. So we know that this is a resonator. It resonates with a certain frequency. And if you build this LC circuit using, let's say, superconducting elements, that there is no resistance, present in it, and you cool down to very low level, for example, 0.00, 1 Kelvin, which means that you eliminate all the noise that is coming into this system from outside, which is, so when you cool this circuit down to this temperature, this essentially is equivalent to isolating your LC circuit. And this is physical circuit that I'm talking about, okay? On your PCB, you can, put some, let's say, aluminum wires, and then you can make an inductor like this, and for capacitor you can give a gap between those aluminum wire, and when you cool this thing down, this aluminum, to this temperature, this becomes a superconducting material. So this is a physical thing that I'm talking about, this LC. So when we cool it down, this essentially means that we are isolating this LC circuit from its surrounding. Now, this is a resonator already, but once we have isolated it from environment and reduced its temperature, this essentially becomes a quantum harmonic oscillator. This was harmonic oscillator already, but by reducing its temperature and isolating it, this is sort of a quantum harmonic oscillator. And if we talk about its potential, you might have seen in your modern physics course that it has a potential profile like this, and this LC circuit can exist in energy levels like this, that it can have an energy equal to half h cut omega, where this is the resonance frequency, 3/2 h cut omega, and so on. So these energy gaps, they are equal. So the system can be here or here or here, depending on the amount of energy present in this resonator. So if you increase the energy, the system can be oscillating here or here, and so on. So this is an example of a quantum system. Another example of a quantum system that we can think about, is a set of trapped ions. If you have a lot of atoms or ions trapped in a magnetic trap, by applying different types of magnetic field, we can trap these ions. And if they're also cooled down to very low temperatures, then these ions can oscillate together. So this is sort of a mechanical oscillator as opposed to electrical oscillator, and this essentially also becomes a quantum system that people use for quantum information processing. Similarly, you can think about photons as a quantum system, and they're actually a really good quantum system because it's very easy to isolate photons from the environment, and also photons don't interact with each other that much that they don't disturb each other. And when we talk about their energy levels, we can think about their polarization state and so on. So one polarization state is one state, the other polarization state is the other state, and so on. So there are these quantum systems that we can use to represent quantum information. Now, to make life easy for implementation and also to reduce the noise and to have a better control over a quantum system, for quantum computers, we work with only two-level quantum system. So for quantum computers, only two-level quantum systems are used, but there's no bar from theory or from any fundamental physics that you can't use three-level system for quantum information processing and so on. Just as there's no bar that if we want to use a three-level classical bits or three-level systems for classical information processing, we can of course definitely do that, but it becomes much harder to design it experimentally and then reduce the errors. So that's why the two-level system is used classically, and similarly for quantum computers, a two-level quantum system is used for quantum information processing, simply because it's much easier to control errors and to have a controlled flow of information on two-level system than any higher level system. So now we have decided that for quantum computers, we will be using a two-level quantum system. Now, unfortunately, in nature, there's no true two-level quantum system. So what we do, we take our general quantum system, which has many levels. For example, this atom, are this oscillator, that we have this multi-level quantum system, but what we do that we only work with two levels of that system. For example, if this is, a harmonic oscillator, or maybe if you think about this hydrogen atom, what you do that you select, okay, I'm going to be working with only these two levels, or you can take, these two levels and so on. And what do I mean by working? Working means that when I interact with this quantum system, I interact with this quantum system through light or electromagnetic waves. So we send a photon of some frequency f. So by restricting this frequency such that this hf corresponds to an energy gap between these two levels, I essentially restrict myself to work with these two levels. Or we can have a quantum system that works with frequency f such that this hf is equal to this energy level, and so on. So if we restrict the frequency of operation, we essentially can work only within two levels. Of course, this means that this harmonic oscillator cannot be used as a quantum computer, because the energy gap between these two levels and energy gap between these two levels and these two levels is the same. So for example, if I have a system here and I send a photon of this energy gap, this photon, can jump, this system can jump to this one. And if I send the photon of same energy, this photon can either jump up or it can jump down because of stimulated emission. So this third level gets involved, and so on. So I have to have a quantum system where the gap between successive energy level is different. So if you want to use hydrogen atom, that's fine, but hydrogen atom has its own problem. So a lot of companies now, especially IBM and many other companies that are building quantum computers, they are actually working with these superconducting oscillator based quantum systems. So to make this system have different energy level, what they do, they just make this circuit non-linear. So when we introduce non-linearity into the circuit using Josephson junction, then what happens that the energy levels of this harmonic oscillators are no longer same. For example, it's like this. So the energy levels become different from each other by introducing non-linearity, essentially changing the harmonic oscillator to a nonlinear harmonic oscillator. So then you can work with these two energy levels. So if a system is in energy level, you send a photon of some frequency which gives energy equal to this photon can jump up. If you send a photon again of this energy by stimulated emission, this can go down, or we can process other we can implement other operations on this using other techniques. Okay, so let me get back. Did
सर आपने कहा कि हम एनर्जी प्रोवाइड करेंगे तो वो ऊपर भी जा सकता है इलेक्ट्रॉन और नीचे भी जा सकता है, तो सर जब हम प्रोवाइड करते हैं तो उसकी एनर्जी इंक्रीज होती है, तो सिर्फ ऊपर नहीं जाना चाहिए?
नहीं, जरूरी नहीं. So when you send a photon of energy gap, first of all, if I send a photon of energy some E, and this energy is equal to this gap, and it's not equal to this gap, so a photon cannot take energy from here and go here. If you have this linear harmonic oscillator, then when a system was here, it can accept a photon to go up, or it can also go down. It will not accept photon, it will emit another photon, but that's okay, because system can be stimulated to go down as well. That's why we have laser, right? In lasers we can prepare system in an upper energy levels, and we can stimulate the system to go down by having photons of exactly the same frequency. So photon cannot always only be absorbed, it can also stimulate the system to emit another photon of the same energy.
ठीक है सर.
Okay, good. Okay, so similarly, when people work with these trapped ions or any other system, the idea is this, that you have a quantum system and you select two energy levels of that quantum system to work with. So you essentially restrict your multi-level quantum system to work with only 2 levels, and that's your, fundamental workhorse of your quantum computer. And this 2-level system is called qubit. So this is qubit. So qubit is not, something very mysterious. It is any quantum system who, has been engineered so as, and you work with it only within 2 levels. So that quantum system is called a qubit, especially when we are, working with the working to build a quantum computer. And there could be, many other examples you can think of. For example, you can think about, if I think about this, hydrogen atom, we know that our electron has spin as well. So if we apply an external magnetic field, then this electron, when it has spin up, its energy is different, and when it's spin down, its energy is different. So which means that we have in this spin system, which is itself part of a larger system. So if in the presence of external magnetic field, each energy level is split into 2 parts. So this has higher energy, this has lower energy, for example. So this can also work as a qubit. So any 2-level system can work as a qubit, but we'll see shortly that what are the desired properties to have in a system that can be used to make a better quantum computer. So why not work with 2 spin levels of hydrogen atom than, let's say, 2 levels of a superconducting oscillating circuit, and so on. Okay, so I hope that have a better idea of what a qubit is, and let's now see the desired properties of the quantum computer to do the task that we were talking about. So what are the desired properties of qubits? Or you can say desired properties of quantum computer hardware. Number 1 is that we should be able to initialize our qubits. For example, when we turn on our quantum computers, we should have a way of starting all of the qubits. So whenever I use the word qubit, I hope you bring the 2-level energy system in your mind, and there can be multiple qubits in one quantum computer, and we will see later that more qubits mean more powerful quantum computer. So when we turn on our quantum computer, we should be initialize the qubits to a given state. It can be any state, but we need to be sure, or we need to be able to initialize our quantum computer to that particular state. For the sake of argument, let's say we should be able to initialize all of our qubits. Now this circle is not something physical. This is just, a schematic representing 1 qubit. So let's say these are my qubits. So when I turn on my computer, I should be able to, suppose, initialize all of them in the ground state. Now this 0 means this energy level, the lower one, and usually 1 mean the upper energy level. 0 doesn't mean 0 energy, or 0, this is just a label for one level, and this 1 is the label for the other level. And we use this label 0 and 1 simply our habit of working with classical bits, where we use 0 and 1 to represent 2 voltage levels or 2 magnetization levels on a hard disk, and so on. So we should be faithfully able to initialize our qubits whenever we need. So that's the first requirement. Okay, and the second is that we should have errors as low as possible. And this is actually still one of the biggest trouble that quantum computers are facing. And let me talk about the sources of errors, so that you get an idea that how we can, choose a system that minimizes these errors. So what are the sources? So if we, think about a quantum system with some energy levels, and this system is of course placed in some hardware. For example, if we talk about hydrogen atom, it's present in space, in our lab or in some device. If we talk about this superconducting quantum qubit, it is present, on a PCB, and it's connected with wires to the infrastructure around it. So this means that this is not a closed quantum system, but it's sort of an open quantum system. It's, interacting with its environment. So each quantum system is present in an environment, which means that the energy is coming in and going out in general. Now, our goal is to have this energy exchange only in a controlled fashion, and that's very hard. And one of the fundamental source of error is the black body radiation. Everything on a given temperature radiates. So anything immediately adjacent to this qubit is radiating an energy spectrum like this. And these photons, so this is black body energy radiation as a function of frequency, and these photons are going everywhere. So this, quantum system is receiving these photons, and they may be, jumping up and down. So that's why the first requirement of building a quantum computer is to cool our quantum computer down to close to 0 Kelvin. Because what will that do? This will reduce this energy spectrum. And the other thing that people then now use to reduce this error is to select a qubit that has an energy spectrum with energy difference, which is, in the microwave region. For example, you are working with some gigahertz of frequency instead of, with light, because this peak, even at 0.1 Kelvin, is closer to the visible range than it is to this microwave regime. So that's why superconducting qubits are becoming popular, because in the microwave region, in the gigahertz part of the spectrum, these black body radiation of the environment are the lowest. They tend to be highest towards the higher frequencies. So this is that's why we cool the system down. So the system cooling is required for two reasons. Number one, many quantum computers are using superconducting material. So for that, you need to have a lower temperature. But there's another reason which is very important, that is that we need to have a quantum computer working at a low temperature to reduce black body radiation, to reduce noise that is entering our qubits. So because this second reason is the reason that why we can't use a higher temperature superconductors to raise the temperature of quantum computer that's working on. Okay, we know that we have materials that can work as superconductors at more than 100 Kelvin, but we are not going to take our quantum computer to work at that temperature, because at that temperature the black body radiation would be even higher. So we are going to keep working at a temperature close to 0 Kelvin to minimize the disturbance of our qubits that are placed in a physical environment. So this physical environment, so this cooling is one thing. The second thing that this physical environment does, that even with all of this cooling and everything, these qubits have to interact with things around it anyway, because it's not just that we need very nice isolated qubits that are initialized to a certain state and that's it. We have to be able to process information. We have to be able to do some operations on them, which means that there are devices that are interacting with our qubits, and because of that, in addition to the intended operation, something unintended is also happening. So that noise is degrading the quantum system. For example, if you have your quantum system at some state go to state 1. So if it is in one state, and even if you leave this qubit on its own, for a good computer, this 1 should remain 1 and it shouldn't be become 0 on its own. But after a while, this can decay. So this is because each state has a decay time. So this qubit can decay to the 0 level, which will induce an error. Additionally, we will see later that we sometimes prepare this system in superposition states, which mean that a system is in some state which is a superposition of this 1 and 0 state. But what happened that after a while, the phase relationship between 1 and 0 that is destroyed. So overall, each qubit has its working lifetime, and we have to make sure that all of our algorithm has to run during that good part of this qubit existence. So if I talk about graph, so as a function of time, our qubit is something like this, that it decays nice, or it remains coherent for a certain amount of time, for example, let's say 1 microsecond, and then it's gone. Which means that if our one gating operation or one logical operation takes 10 nanosecond, I can only do 100 logical operations, or I can apply 100 gates on this qubit. And even then, with the passage of time, the noise is creeping up because of this decoherence. So one is this temperature. The other thing is this this decoherence. So each qubit has this decoherence time, and we have to work within that time. People are trying to increase this coherence time as much as they can. And just to give you an idea, that 10 years ago, this was like 100 nanosecond or something like that. And now it's gone to more than 1 microsecond. And the hope is this, that in the next few years, this can be extended to 10 to 100 microsecond, that we should be able to apply thousands of quantum gates on our qubits before they are destroyed. Okay, and then there's another source of error. This is called measurement errors. That even if our quantum system is intact, it's in the state that it is supposed to be, when we try to measure our system, then there are measurements errors. For example, if the system was in one state, most of the time you would measure it to be 1, but sometime you can measure it to be 0. It's different from the collapse of the system to the state that I was talking about earlier, that when we measure from superposition state, it can go to 1 or 0. This is, even if the system is already in 0 and it's right there, there can be error in measuring the state as well. So the desired properties of any quantum computer is essentially these three with this when we talk about a single qubit. Now, another property that we desire is what is called the entangling operations. That when we talk about 2 qubits, we should be able to make logical operations on these qubits that depend on each other. That the final state is not something of this and this, but it is a joint state of these 2 qubits. We'll talk more about it later on. So these are called entangling operations. So we should select a system where it's easier to perform these entangling operations. And actually, that's why these superconducting quantum computers are being preferred over other types of quantum computers, because it's much easier to perform these entangling operations on them, and in a more controlled fashion than in many other possible candidates of quantum computers. Okay, so any questions so far? If not, let me talk about quantum gates.
मुझे अगर आप entangling operations दोबारा समझा दें.
So entangling operation ऐसा operation होता है जिसमें you are trying to come up with a state of 2 qubits, suppose, So let's say we're talking about 2 qubits, that the final state is a joint state of those 2 qubits. It's not a state of 1 qubit and a state of the other qubit. So you can think about like this. If let's say you have 2 things, and you can talk about them like this, that okay, this thing has this color and this is its weight and so on, and the other thing has this color and its weight is so much and so on. We say that these two are unentangled because you can talk about them independently. But instead, if you know you have to describe their properties in a joint fashion, there's no way of talking about them separately, then that's an entangled state. It's not possible to give a classical example of this, because in classical you can always distinguish different things, and you can always talk about, okay, this qubit is in 1 state or 0 state, or something like this, or this qubit this. But in quantum mechanics, we can construct these joint states. These are called entangled states, and we'll see operations that can prepare these entangled states later on.
Thank you, sir.
So for now, you can think that we need a hardware that can enable these joint operations.
Thank you, sir.
Okay, thank you. Okay, so let me now briefly talk about quantum algorithms. So you can picture a quantum algorithm like this. It's different than classical algorithms. So in certain sense. So, and that's what I'm going to talk about. You can think about it like this, that you have a bunch of qubits. So these circles I'm using schematically to represent qubit. This itself can be, a trapline system, and this could be, those 2 levels in that and so on. And this could be, if we talk about superconducting quantum system, then you can picture it like this, where I make these 3 qubits, that there is 1 oscillator here, there is another, of course, there are nonlinear, oscillators, and so on. So these are physical qubits separately. So a quantum algorithm is, a sequence of operations, something, and these individual operations are called gate. There may be, some these conditional gates or entangling operations that I was talking about. So you do something to this, you do something to this, you do something to this, you do something jointly to this. So physically the systems are there, you are doing operations on them. So schematically I can represent them, using these gates and so on. So at the end, you measure their state. So this meter is, sort of measuring thing. And these 2 lines are used for classical information. So there was, these qubits were in some initial state, and then we did a bunch of operations on them, and then we measured them. So this is how a quantum algorithm is viewed. That it's a sequence of operations on these quantum bits. And later on, we will see that when we want to do, something practical, classically we think about a sequence of operation. Okay, do this or do that, then do this or do that, and so on. And at the end, we have a certain result. But when we talk about quantum computers, we have to think about the quantum algorithm as a process of increasing probabilities of certain outcomes and decreasing probabilities of the other outcomes that you don't want. Okay, so when we talk about these individual operations, these individual operations are these quantum gates. They can be, something like this. For example, your system is present in this 0 level, and you do some operation on it, and it is transformed in certain way that your system go to state 1. So this is one type of operation. Or if your system is present in, for example, one state, and you want to transform it to zero state. So this is one type of operation where you sort of invert. You take system from 0 to 1 or 1 to 0. This operation is called NOT operation or X operation. So this symbolically this is represented by this X gate. Similarly, let's say we have a system like this, that your system is in 0 state, or your system is one state. And let's talk about this operation. So this is an operation in which you don't do anything if your system is in 0 state, but you multiply the one state with this minus number. So this is essentially equal to giving it a phase of 180 degree, because exponential iota pi is -1. So this is like a phase flip gate. So this is called a Z gate, and so on. So it has a symbol of this Z, and so on. And we'll talk about many other gates like this later on. So after a while we'll stop talking about energy levels and so on, but at the back end, that's what is happening. Okay, so any questions so far? If not, let me talk about quickly about applications. And some of these applications we are going to be covering in this course. The most important, or perhaps important in the sense of driving research in quantum computer, is application in quantum chemistry or quantum physics. Quantum chemistry or quantum physics deals with these things. For example, you are given a molecule, you have a hydrogen molecule, there are 2 electrons going around it, and you want to find out its ground state energy. Or you have, let's say, hemoglobin molecule, there are a bunch of nuclei, and there are a bunch of electrons going around, and there are there could be hundreds of atoms and thousands of electrons present in this molecule, and you want to compute its energy levels. And this is important because when you are designing another drug, that is also a molecule. Okay, so and you want to compute its energy profile as well, because from these energy profiles you can find out if this drug is going to act on hemoglobin or not. For example, this is a drug that you're designing for something, some disease in your body, but you also want to see that this drug doesn't do any damage to other things that are present in your body. So this is, for example, one example. This is hemoglobin, and this is some drug. So these computation of energy levels of these molecules an extremely important part of quantum chemistry and quantum biophysics. And this is a very difficult problem classically. You need exponentially large number of resources to be able to measure it. And we'll see a little bit later that why, when we do the matrix representation of qubits and operators. So this is a classically hard problem because you need exponentially many qubits and exponential time in working out this quantum mechanical problem. So this is one problem which is driving a huge amount of research in quantum computer, because with only few hundred qubits, we will be able to efficiently simulate the energy profiles of these bigger molecules. So in roughly the number of qubits required scale proportional to the number of electrons in your molecule that you want to include in your simulation. On classical computer, it requires the resources which are exponential to the number of electrons. For example, if you have 100 electrons, roughly speaking, you need 2 power 100 bits for your classical computation. But for quantum computer, your qubits required are only proportional to 100, for example, 200, 300, and so on. So that's, one thing that also led to the proposal of quantum computers in first place by many people like Feynman, Benioff, Manin, and a couple of other people. So it was natural for people to ask that to simulate a quantum system, if you have a quantum computer, you can simulate it efficiently, because it's been known for a long time that quantum systems cannot be simulated efficiently on classical computers. And by the way, if they can be, you don't need to build a quantum computer, because if you can simulate a quantum computer on your laptop, why do you need a quantum computer to begin with? And you need, there's no problem in simulating, okay, let me put it that way, but you need exponentially many resources. For example, perhaps you can simulate a 40-50 qubit quantum computer on one of the large supercomputer, but if you go to 100 qubit, the current computers that are available, they're not enough to simulate a 100 qubit quantum computer. But if you are able to build, 100 qubit, so this also means that if you're able to build a 100 qubit quantum computer, you are already, ahead of the currently available supercomputers. Okay, so this is one application, and unfortunately, this is something that we are not going to talk about in this course, because this requires knowledge of quantum physics to be able to do this. But I would also like to point out for people who are from physics, and perhaps for the other people as well, that don't think that only these molecules and these systems can be simulated efficiently in quantum computer. Lot of quantum mechanical process, for example, what is happening at the LHC, where you're colliding protons, neutrons, and other particles together, to discover new physics. Those processes can also be efficiently simulated on a quantum computer. Similarly, other quantum electrodynamical processes and that are hard to simulate classically, they can be simulated on these quantum computers. So in addition to quantum chemistry or simulation of molecule, a lot of work is being done to develop algorithms to efficiently simulate other quantum physical processes on quantum computers. The second, set of applications relates to searching algorithm. So people have discovered algorithms that are faster than classical algorithms. So there's a lot of interest from Google and many other companies, Amazon, and especially these companies who rely on searching efficiently through databases, that they're investing money into building these quantum computers, because it's not exponential speed up. It's not as dramatic as this molecular chemistry that I was talking about, but this is still a speed up good enough that that is worth investing money. That's what these people are thinking. And this is an algorithm. This is Shor's, sorry, not Shor, Groover search algorithm, and we will discuss this thing in detail, because this doesn't require quantum physics, and we'll be able to do it very elegantly in a very good way. And this quantum search algorithm by Grover can also be used to develop algorithm for many satisfiability problems as well. And we will talk about that as well. Another part of algorithms is based on Fourier transform. Since Fourier transform, is used to analyze periodic signal. For example, you can find periodicity in images and audio or video signals by doing this Fourier analysis. So people have discovered that Fourier transform on quantum computer can be accomplished faster than on classical computer. So a lot of algorithms have been developed that utilize Fourier transform to build efficient and faster quantum algorithm. And we will study this, and especially Shor's factoring algorithm, because factoring is considered to be a hard problem on classical computers. So we will discuss this algorithm also in detail. And recently, people have been working on developing efficient quantum machine learning algorithms using quantum computers. So there's a lot of interest in this area as well, because this is thought to be an area where you can get quantum advantage with lower number of quantum bits. So this is also, unfortunately, an area that we will not be working on in this course. Then there is another part of application. It's quantum algebra. People have discovered faster algorithm to solve, let's say, simultaneous simultaneous set of equations, and we will discuss that algorithm and implement in this course as well. That relates to quantum algorithms, quantum algebra. And then there are applications in optimization problems. So efficient optimization algorithms have been developed. And if we have time in this course, I will present the quantum approximate optimization algorithm that you can see that can optimize faster than classical computers. Okay, so this concludes the introduction to quantum computers today. So if you have any question, please do let me know. Otherwise, we will have a 10-minute break.